Hello students, I am Purwar and I welcome you all in this tutorial, and today I am going to discuss a very important question that is based on the Young's double slit experiment. Okay, in the previous video I have taught you what is the Young's double slit experiment, how the fringe patterns formed on the screen. Now we are going to discuss a question that is based on the Young's double slit experiment. Stay tuned and focus on the board. So the question is, a source emitting light of wavelength 480 nanometer and 600 nanometer is used in a double slit interference experiment. Okay, so the two lights have been given. Now the separation between the slits is 0.25 mm. So separation between two slits that are used in the YDSE are 0.2 mm. And the interference is observed on the screen placed as 150 centimeter from the slits. So capital D is given is 150 centimeters. Great. Find the linear separation between the first maxima corresponding to the two wavelengths. So here two wavelengths are given. So first we have to calculate the first maxima corresponding to first wavelength, and then we have to calculate the first maxima corresponding to the second wavelength, and then we will calculate the separation between them, linear separation between these two maxima corresponding to different wavelengths. Great. Great. Now let's understand this. So see this diagram. So in this diagram, I am incidenting light like this, and these are two slits. This is slit S1 and this is slit S2. Now from these two slits, light is emitting, and corresponding to lambda 1, I am considering lambda 1 is equal to 480 nanometer and lambda 2 is equal to 600 nanometer. Right, two wavelengths 480 nanometer and 600 nanometer are given. Great. So for lambda 1, the light waves are getting interfered at point P and they are making a first maxima. Okay. And corresponding to wavelength lambda 2, two waves are getting interfered at point Q and they are making first maxima corresponding to lambda 2 there at point Q. Okay. So from the central maxima, I have considered that the distance of this point P from the central maxima is y11. Why y11? One is for first maxima and second one is for lambda 1, because this is for lambda 1 wavelength. And here the distance of point Q from central maxima is y12. 1 is for the first maxima and 2 is for the lambda 2, because this is corresponding to lambda 2. Okay, so these are two distance from the central maxima corresponding to wavelength lambda 1 and lambda 2. Okay, and the distance between and the distance of slits and screen is capital D, and that is 150 centimeter that is given. So I will convert this capital D in meters. So this capital D will be 1.5 meters. Great. And the separation between the slits is given 0.25 millimeter. Again, I will convert this small d in meter. So that will be 10 to the power minus 3 meter. Okay. So now let's calculate the distance of first maxima from the central maxima corresponding to each wavelength. So first I will calculate for lambda 1 wavelength. Okay. So for lambda 1 wavelength, we know condition for maxima. I am assuming that you understand the basics of interference and YDSE. Okay, great. The condition of maxima is d sin theta is equal to n lambda, or we can write sin theta is equal to by n upon capital D. Here by n is the distance of nth maxima from the central maxima, and capital D is the distance of screen from the two slits, is equal to n lambda. So from this we can write yn is equal to n lambda capital D upon small d. Great. Now here I am calculating this for lambda 1. So and also I am calculated for first maxima, right? right? So for first maxima, what will be the value of n? N will be equal to 1. Great. So put the value of n. So I am calculating for lambda 1. So here I will put by 1 because I have already considered this y11. So n will be equal to 1 and lambda will be equal to 480 nanometers. So I will convert nanometer into meter. So that will be 10 to the power 9, right? And capital D is 1.5 meter, right? Divided by what is the value of small d? That is 0.25 into 10 to the power minus 3, right? So now let's calculate the value of y11 first. So y11 will be equal to 480 into 1.5 into 10 to the power minus 9 divided by. Now I am just taking this point here, so I can write this as 25 into 10 to the power minus 5. So this will come out to be 480 into 1.5 divided by 25 into 10 to the power minus 4. Okay. Okay. So here I am using calculator and will tell you what will be the value of this. So give me a second. So it will be 480 into 1.5 divided by 25. So this will be 28.8 into 10 to the power minus 4 meter. Okay. Okay, great. So call this as equation 1. Great. Now for lambda 2 wavelength. Okay. Again, similarly, you have to calculate. We know the condition. The condition is same. D sin theta is equal to n lambda. So it will be again yn is equal to n lambda capital D upon small d. So here for the first maxima, corresponding to lambda 2 wavelength, n will be equal to 1, right? So put here, but here I will put y12 because I have already considered it y12. Great. And I will put n is equal to 1 and lambda here is 600 because lambda 2 is 600. Okay. Here I will put that lambda 2 is 600 nanometer. If I have to convert it into meter, then it will be 600 into 10 to the power minus 9 meter. Great. So put the value of lambda 2 into in meter. Okay. And capital D is again 1.5 and small t is again 0.25 into 10 to the power minus 3. So everything is same. So this will come out to be, let me again use the calculator, 600 into 1.5 divided by 25. So it will come out to 36 into 10 to the power minus 4 meter. Okay. Y11 came out to be 28.8 into 10 to the power minus 4 meter, and this came out to be 36 into 10 to the power minus 4 meter. This is equation second. So now we have to calculate the linear separation between these two maxima corresponding to wavelengths lambda 1 and lambda 2 respectively. So what we have to do? So the linear separation will be delta by, and that will be is equal to y12 minus y11. So now put this value y12 from equation second, that will be 36 into 10 to the power minus 4 and 28.8 into 10 to the power minus 4. Great. So how much this will be? Delta y will be equal to 7.2 into 10 to the power minus 4 meter, or if you want to change it into millimeter, then it will be 7.1 into 10 to the power minus 1 millimeter. So you can write it 0.72 millimeter. Okay. So this will be your answer. Delta y is equal to 0.72 millimeter. So I am putting it in the box so that you get the better idea. So this will be your answer. Okay. This will be your answer. Okay. I hope you have understood this. Thank you. Bye bye.